Okay, hello all. Today we'll be looking at the topic fuzzy controllers and the various types of methods for fuzzy inference system. So basically, in the last lecture, we looked at what is a fuzzy inference system and the different ways and different steps of finding out after defuzzification, finding out a crisp output given a crisp input. So fuzzy controllers are also for controlling and any sort of decision-making system. They typically use fuzzy linguistic descriptors for controlling the entire physical process. It was actually introduced by Ibrahim Mamdani and Asilian in 1974-75 for creating a model of a steam engine. And we can see many such kind of fuzzy inference systems or fuzzy controllers in air conditions, washing machine, cruise controls, blast furnaces, etc. So fuzzy controllers basically use the fuzzy inference principle to map a particular input that is given so that based on without any training or learning mechanisms like we have in neural networks, how can we map a particular input? Given a particular input, how do we get a particular output? So the basic structure of a fuzzy controller looks like this. It you'll have so in order to develop the entire system, you'll be having some input where the input may be automatically done with the help of a sensor. So you can say you can have some sensor data or any other input that is given by the operator or user, and that we convert it into to through an input stage where we do the fuzzification process so that every input is mapped to some membership values. So we know that process is basically known as fuzzification. And we have already seen the basic structure of a fuzzy inference system. The same thing is, it is this figure that is shown here is similar to that. It's because the first step is fuzzification and the second step is basically the knowledge base where the role evaluation is done. And the last step is the defuzzification, which converts a fuzzy input to a fuzzy input that comes into the output stage to a crisp output after defuzzification. So the processing stage here that you see, it uses a fuzzy rule base that consists of fuzzy logic rules like if then rules. So for example, if the room temperature is cool, then the heater is high. So you have got linguistic descriptors here as well as the fuzzy nature like cool and high, etc. Okay. So then the output stage, it converts or combines all these results and then maps them to a particular crisp output. That is with the help of defuzzification functions that we saw in the last lecture, like center of gravity or centroid, center of sums, and then the MOM method. So we looked at those in the previous lecture. Now, expanding these three steps once again, fuzzy rule base, all of you, we all know that it will be some rule of the form uh, if a particular variable x is given input and a variable y is given, and you have a fuzzy set A that is given as the that fuzzy set A, and then we have a fuzzy set B. So you have two variables x and y and fuzzy sets A and B. Then if we say that if x is A, then y is B. This is a very simple rule which consists of antecedents and what do you say consequence. Okay, now the antecedent part is the if part that we already know. The if part is the antecedent and the consequent is what comes after the then part. For example, the room temperature is cool is the antecedent and the heater is high is the consequent. So you can have not just simple rules like this, we can also have more complex rules. This is a single rule which will have a number of antecedents. You'll have x is a. The format of x is a is there in many uh, ways, and you can see a simple rule that is shown there. So if x1 is a1 and x2 is a2, etc., etc., xk is ak, then y is b. Now, the input stage, also known as the fuzzification, if we have given a crisp input as the value, then we map it to the truth values or the membership values that are basically fuzzy sets. So, say for example, you have an input x1 is 30 degrees Celsius, then the truth value for the fuzzy set cool maybe the membership may be mapped to value say 0.6, and warm, the membership value may be, or the truth value may be 0.4. Okay, so the truth values will be calculated for all fuzzy sets of the input values. That is, from if you have multiple like x1, x2, x3, xk, etc., then for all of them we'll have a set of mapping to the fuzzy sets. And the processing stage is basically firing of the rules. So given a set of input that is mapped to a membership or a truth value, and how do we know which should be taken? What is the rule that should be accepted? So those rules are known as the fired rules. So looking at the knowledge base or the rule base so that we get a particular output. So which rules should be fired based on the input values? So what we do here is you'll have maybe multiple. You can see here it's connected with the help of the different antecedents are connected with the help of operators like and or. So based on that, if there are multiple rules, then we need to combine the antecedent truth values. So say for example, the common one we know is we have seen here. The rule evaluation is done with the help of and. If it is you're using and, then you use the minimum. If it was or, use the maximum. So this rule evaluation procedure is done with the help of these logical operators, which evaluates to minimum or maximum based on the logical operator. And once we are done with this rule evaluation and it's summarizing together, then what we do is we apply these results to the consequent part, because we had this antecedent. So whenever we have multiple rules here, so we determine which of the rules has to be fired. Once it has been determined, then we should be able to apply the rule on the consequent part, that is y is b. This is b is also a fuzzy set. So we'll be able to apply it to a consequent fuzzy set. And usually, if it's a Mamdani system, the min operation, that is known as the implication part. So getting the implication after the role evaluation, we need to do an implication. Usually, we use a min operation there. You know, that is the min max composition will be used, or you can also use a max product composition that we learned in the previous classes. And finally, you'll be getting a output variable. So if there is one rule, you'll get a simple output variable like this. So depending on how many rules are there, you may have a number of output variables. So finally, defuzzification, the last block, it converts these fuzzy outputs. So maybe it can be a single output or it can be multiple outputs, and they need to be aggregated together. They have to be aggregated together. And finally, we have to convert it into crisp values. So all the fired rules that results in the output will be combined together so that we get a particular crisp value for controlling the fuzzy controller is developing a system, right? So finally, you should have, for a particular crisp input, we should have a output which determines uh, what is the what does the result that is to be achieved. So finally, for defuzzification, these are the different methods where we have already seen centroid, center of gravity, then mean of maximum or center of sums, etc. So the designer of the system may choose the most appropriate one. So this is a detailed block diagram of what we saw here. The same thing, but in a detailed manner. So you can see the sensor input is given here. Then you have fuzzy membership functions for the antecedents, and we perform a fuzzification based on these truth values. And in the processing, we'll be looking at the fuzzy rule base. And in some of the systems, you may have a fuzzy associative memory where you'll have a table of all the linguistic descriptions that are given. Then fuzzy set memberships for the consequent is applied here while after the processing. Then finally, the output stage, some defuzzification strategy will be selected, and we'll do a aggregation here also. And finally, we get the output for controlling the system. So there are various applications of fuzzy controllers already mentioned in the introduction, like industrial applications, then consumer electronics, any advanced systems, especially mobile robots is a very common area where fuzzy controllers are used, those controls as well as mobile robots. So we'll be looking at one of the examples. These are the two examples given in your textbook. We'll be looking at the fuzzy air condition controller, where the input given will be the room temperature and the output will be a. So you can have more than one inputs, but maybe a single output only. Usually the case is like that. So here also in the cruise controller, you can see you have speed as well as the acceleration as the input, and whereas the braking control is given as the output. Okay. So let us look at the first example, that is a fuzzy air condition controller. So I've keeping the extract or screenshots of the textbook in order to make you understand how this works. And this is basically the Mam Mamdani system itself. The basic idea of this fuzzy controller was introduced by Mamdani. So when the Mamdani method is asked, you can also write this. So just consider a simplified version of air condition. So it keeps tracks of the room temperature, you can see here, and it regulates the temperature of the air. So the purpose is to maintain the room temperature at a predefined value, that is our aim. So we assume that the AC does not regulate the flow of air into the room, but only the temperature of the air. Okay, only the temperature has to be controlled. Now let T0 be the desired room temperature. Suppose we need a particular room temperature. Then the air condition has the thermometer. So in order to measure the input, you need some sensor, right? So you have a thermometer that measures the current room temperature T. Okay, so this is our decide. So we want the room to be this much cool, say T0. Okay, we want it to be 18 degree or 19 degree, but currently it is, you can say 24 degree or something. So the difference in the temperature delta T is the current temperature minus the target temperature. So that is the input that is given to the controller. So what we give as input to the controller is the difference in the temperature. When the difference is positive, that it is greater than zero, that means what? The current temperature is too high than the target. Target temperature is basically we want to keep the room cool, so the temperature will be lower, right? So if you have a higher temperature, that means you currently the room is you can say hot towards tendency towards the hotter climate, and inside the room when the target is we want to cool the room. So if suppose delta T is greater than zero, then we say the room is hotter than the desired temperature. So what the AC has to do, it has to blow cool air into the room so that the temperature of the room comes down to T0. Okay. Now, so when delta T is greater than zero, the output should be, you can say you have to have a cool air as output of the air, not output. You can say the AC has to blow the cool air. Now that is not the output here. I'll show you what is the output in the next paragraph. So now on the other hand, when delta T is less than zero, that means what? The room is already cool. So much cooler than the target. Say it was, say we expected around 18 degree, but the current temperature is 17 or 16. That means you got a negative value in the difference. So then it is too cool. It's too cold. So it will be uh, very cold. So what we can do is we can warm up the room by blowing, the AC should blow up a hot air into the room. So this AC has both cool air as well as hot air. And if it is less than zero, you do this. Now, in order to achieve this, we need that something should be controlled, right? So how do you know whether you have, once the sensor gets the reading, how do you know that cold air has to be blown or the hot air? So in order to achieve the required temperature, the air to be blown into the room is actually controlled by a dial. You can see this. And this is the input, the dial. So its position will vary. You can say the dial positions will vary from -1 to +1. So what happens here is this positive value, if you can see here, and a positive value, if zero means you're not the no air will be blown. When you can see this arrow that is showing when it is at zero position, that means no air will be blown from the AC. But when it is moving towards a positive direction, that is from 0 to +1, that means hot air will be blown. So when do we need a hot air? When delta T was less than 0. So whenever you have a temperature difference of less than 0, the dial should move in the positive direction so that hot air can be blown. And whenever you have a, what you say, value where delta T is greater than 0, that means you need to cool the room. So you need to do the dial should be turned towards -1, indicating the degree of cold air that is to be blown from the AC. So you can see here, over here, the degree of cold air is determined, and direction when it is positive, the degree of hot air is determined. So you can see it is the opposites. When the value is greater than 0, you go move on to the negative side, but when the value delta T is less than 0, you move on to the positive side. So remember this in mind. Now, when it is a 0, no air will be blown. So the input to the fuzzy controller, that is T is delta T is equal to T minus T0, and that is the input to the fuzzy controller. So what is the input? So if you have a fuzzy controller logic system here, and the input to this will be delta T. And what is the output? Output is the position of the dial. So this is what we need to control. So based on the input sensor value, I need to control the dial so that I can cool the room or I can warm the room. So that is a basic idea. Okay. So here you can see both. So when we talk of these systems, it need not be that the values need usually we talk of crisp values as input, and finally we need crisp values as output, right? So there's a possibility that you can also have fuzzy values as input, and finally without defuzzification, the step before defuzzification, you have a fuzzy output. You can directly take that output in without doing any defuzzification process. So that is also possible. But in our case, we are using a real-time scenario where you want to control air condition. So we expect that these values, delta T and D, has to be crisp in nature. Okay, so in between, the fuzzy things are by fuzzification and defuzzification, we convert to and fro. Now, okay, now we'll look at the different steps involved in this. So what are the fuzzy sets in this? That is what we are going to find out now. So occasionally for a fuzzy control system, you can see it is convenient to categorize the strength of the input and the output parameters with the help of certain fuzzy sets that is usually referred to. You can see these sets are very commonly used in most of these names. These linguistic descriptions are commonly used, like large negative, that is denoted by LN, medium negative, and small negative. It shows large negative is what you say on the negative side too much, then medium negative and small negative. Then for the neutral state, you have something known as 0. Then you have small positive, medium positive, and towards the positive end, goes from small, medium, large. And towards the negative end, it goes from small negative, medium negative to larger negative. So these are the magnitude of the respective parameters in the for the context of the given application. So if they're giving you another example, maybe these terms may not match there. So depending on what is your controller you want to design, you have to find out terms like this. Okay, so for the system, now what we are going to do is for both the parameters, we can use these terms for delta T as well as for D. D is the dial position. So all the five of them are applicable for both the type of input and output. Okay. Now, uh, let us draw two membership profiles. We are assuming these are the membership profiles. So when you are trying to design your own system, you have to find out the appropriate values. And for the membership, you can see here this one. So this is delta T in degree Celsius. And when you can see that when the value varies from, you can say minus infinity to -3, you can say it is large negative. And when the value is between -6 to 0, it is medium negative. When the value is between -3 to 3, with the 0 being exactly mapped at the peak point of ZD, you can see here, it is 0. 0 denoted by ZE. Then 0 to 6 is denoted by medium negative, and large positive, sorry, not medium negative, sorry, medium positive. Then large positive is 3 onwards, 3 to infinity, you can say. So this is the basic idea. So you can say the membership increases uniformly as delta T increases from 0 to 3. That is in this case. For example, you're taking the membership of delta T in medium positive. So the membership of delta T in medium positive is 0 for delta T less than equal to 0. So whenever the delta T value is less than equal to 0, you can see that medium positive starts from 0. See this graph? It starts from here. So whenever you are beyond this point, the membership value of medium positive where delta T is less than equal to 0, you don't have any membership there. It always starts from 0 till it moves on till 6. So it is 0 for when it is less than 0 and for greater than 6. So when you are looking at the points greater than 6, here also the medium positive is not. So medium positive varies only from 0 to 6, not beyond this, and not even here also, not beyond this also. Okay. So this is the basic idea. And you can see the um, same applies for D also here. Yeah, here also it becomes the same thing. You can see from here till here, 0 to 1, medium positive is there. But when the value is negative, it is the membership. Medium positive is not applicable for negative values. The same thing. So now let us create. So this was how we design the linguistic variables and its corresponding fuzzy membership values. We have drawn a graph for this for both delta t as well as delta, not delta, sorry, d, the dial. So you can see the dial is large negative and the value is less than minus 0.5, and it is between -1 and 0, then you say it is medium negative. It is between minus half, minus 0.5 and plus 0.5, it is 0. Between 0 and 1, it is medium positive. And greater than plus 0.5, it is large positive. Okay, so this is how we did for D. Now let us look at the fuzzy rule base. The system under consideration here is a simple rule base consisting of 5 rules. So we don't have a single rule, we have multiple rules. So we label them as R1 to R5. Now it is given here when delta T is ln, then D is LP. You can look at the graph. So let us look at the graph. When delta T is ln, you look at that. When delta T is what to say, the large negative, then naturally D should be large positive. The opposite, because we already saw in this previous case, whenever you need a value that is, yeah, delta T means the difference, right? When the difference is less than equal to 0, what was less than equal to 0? See here, the difference when it is less than equal to 0, I told you what we have to do. That means that the room needs to be warmed up. When the room needs to be warmed up, what is the direction of the dial? The dial has to go in the positive direction. So you have to reach up to the point +1. Then only you can have hot air to be blown into the room. That means the room is already chill. So if the room is already cold, then you need to move in the positive direction in the on the membership functions of D. Okay. Similarly, the next one, when the delta T is Mn, the next one, delta T is medium negative, then you have to move in the medium positive direction. So when it is medium negative, you have to move in the medium positive direction. When it is 0, it is neutral, the same thing, 0 itself. But when it is medium positive, that means the room is already somewhere. You can say it is much hotter than. So still here you had a cool room, but now it is hot in this direction. So then what you have to do is you have to change the dial to the negative direction so that you get cold air. Okay, so when it is medium positive, then the dial should be moved in the negative direction so that you get cold air. So that is medium negative. Okay, when the delta T value is large positive, that is, it is very hot inside the room, then you have to move to the extreme end of the negative direction for the dial so that maximum cold air is drawn, and it should be large negative. Okay, so you can see that it's opposites of the graph goes in different directions. So the block diagram of this is shown in figure 4.16. You can see here the same thing. The input given is delta T and the output that we need is the dial position. So after fussification, these are the different fuzzy set values we need to map to. And for each of the rule, we'll be mapping them to a particular D value fuzzy set. And after defussification, we have we have the output D. Okay, so this is the basic idea. So depending on the result of this, the entire description is given here. You can just read through it. Now we are going to, this is the question in hand, that is we given a fuzzy set and given a fuzzy rule base. We need to find a particular crisp output for the crisp input value delta T is equal to -2. Suppose that the difference between the actual room temperature and the targeted room temperature is -2. That means delta T is less than equal to 0. What should be the dial position T in order to achieve a target T0? So that is our question. Okay. Now moving on to uh, classification. We need to find out for this given question delta T is equal to -2. We need to compute the degree of membership of delta T with respect to all of the 5 fuzzy sets. So we are going to find out what when T is equal to -2. So let us mark -2 here. This is the point -2. Okay. When T is equal to -2, you can see that large negative does not have any, the graph, you can see the large negative graph does not have any intersection with the point -2. Similarly, medium positive as well as large positive, all these are beyond -2. So you do not have any membership in this particular fuzzy set with the for the member -2. So you can write mu of delta t mu of for ln of -2. That is the variable x is -2 here. The x-axis is -2. That is delta t is 0. Similarly, for MP also it is 0. For LP also it is 0. So you can see these three graphs does not have any membership value or any role in being the member of -2. Whereas the other two, that is MN, medium negative and 0, has a particular membership value. Now you can see here it's -2. It is given by 2 by 3. That is the point where it intersects. So you draw a line that intersects at this slope of Mn, and you can see that is around 2 by 3. Then when you look at the Z0 graph for -2, it comes to that is 0.67 is the value. When it comes to it comes the for ZD, it comes to around 1 by 3. That is 0.33. That is this point. Okay, so how do you find out these y coordinates? So you know that the x-axis is the delta t, x is the delta t value, and the y-axis is the membership value. Okay, y-axis is the membership value which varies from 0 to 1. Okay, now next step is how do we find out these values? Okay, so in order to do this, we need to have uh, find out the y coordinate given x coordinate by looking at the linear interpolation. So we need to find, so given the x coordinates, and we need to find where in this graph, maybe either in a descending slope or in a ascending slope. So you can see this is the ascending part of the slope and this is the descending part of the slope. So you can see one of them meets in the ascending part of ZE and the other one meets in the descending part of MN, right? So one is over here and one is over here. So we need to find the linear interpolation on these slopes, and basically the formula for linear interpolation is given by okay. So we need to find out for only these two, and we need to find out what are these 2 points. So basically the linear interpolation, so given a value for a particular points that are given x1, y1, x2, y2, and given a new point x, we need to find the y coordinate for that. So y is equal to y1 plus x minus x1 by x2 minus x1 into y2 minus y1. So this is what we need to find out. So given x1, y1 a point, That is maybe this, if you're looking at the descending slope, this is the starting point x1, y1. This is another point x2, y2. Then suppose I'm giving you a point x that is -2. I need to find where on this line it is going to intersect. So I need to find that y point. Okay, so that is what we are trying to find out. So I'll just repeat it again. Given a point x1, y1, maybe this one, and another point x2, y2 that is determined by this line, that is the slope here. And I'm giving you a point x that is -2. I need to find where on this line this particular -2 is going to intersect when you draw a line parallel to it, where it is going to intersect on this particular line. We need to find the corresponding y value for that. So the equation is basically like this. So x1, y1 is the coordinate of the first known point, x2, y2 is the coordinate of the second known point. X is the input that we are given, for which we are correspondingly we are trying to find out the output. So when it comes to this fuzzy concept, you can just ignore this y1 like that. We can then simply write it in this way. That is, if it is a ascending slope, I'll just write it here. If you have a ascending slope, then we can write it as mu of a particular value that we're trying to find out. Okay, membership of the particular value. Membership of the particular value x means, suppose this is x -2. What is mu of -2 is nothing but the y coordinate, right? So that means it is equivalent to writing as y. Okay, is equal to, we need to have a starting point y1. Y1 means what? That is, this is the mu that this axis is known as a mu, right? Mu of x. So we write as mu start, the starting point of the first point. Okay, x1, y1. Y1 is the y-axis of the first known point. So x start plus x minus the starting. So every one has been replaced by the starting point, or you can simply write x1, no problem. And then you can write, and the second x2 is written as x end and x start. Okay, so these are the points. And then you need to have y1 and y2. Y1 and y2 in our case, it is mu of end minus mu of start. So this is a basic idea of the slope that we are trying to find out. Okay. Now, how do we, and I'll write the equation for the second one also, the descending slope also. Then we'll move on to find out how we did this. So this for the descending slope, this is okay, ascending slope is actually this one, this is the ascending slope. So for this one you have to use this equation, that is finding out 1 by 3, the answer 1 by 3 we get in ascending slope. And for this particular mn graph we are going to use this descending slope, and that is we will be getting the answer as 2 by 3. So when it is a descending slope you have to change it like this. So because it is descending you will be subtracting it instead of adding. So you have mu start minus the same thing, x minus x start divided by x end minus x start into, because it is a descending slope, we have to first write the starting value and then the ending value. This you can understand by looking at these points. I'll just be on. So if this is -2, you can see here, this is x end minus x start. Why? Because in ascending slope, the starting point value, you can see here, it is lesser than the ending point value. So when you look at the y coordinate here is 0, whereas here the y coordinate is 1. So you should have something like 1 minus 0 here. Okay. And when you look at the descending slope, you can see that the starting point of the y coordinate is actually lesser, um, sorry, greater, and the ending point is over here. Because it is a descending slope, you are moving from a higher point to a lower point, right? That is why it is known as descending. So the starting point here will be 1 and the ending point here will be 0. So in both cases, it is 1 minus 0, that is, it's multiplied by 1, which has no effect. Okay. So that is what is done here. So you have a starting point of y in as 1 here and the ending point as 0 here. In the opposite direction, you have a starting point 0 and the ending point 1 here. So that is why we write it in the opposite so that we don't get a negative value. We get mu end minus mu start and then we have mu start minus mu. So remember this formula, the difference here is only the reversal of these values and you have a minus here and a plus here. The rest are the same. Okay. Now moving on. Let us find the slope of any one of them and then say, I'll erase this. Okay, so this is minus 2. Now for ascending slope, our equation was mu of x is given by mu start plus x minus x start divided by x end minus x start into mu end minus mu start. Okay, so this is our point. Now let us find the first one, that is the ascending slope for this. So this is the ascending slope, right? I'm just going to mark it in red. This is the ascending slope. And you can see the coordinate here is minus 3 and 0. So you can see the first coordinate x1 or x start and y start. What is x start and y start is nothing but minus 3 and 0. And whereas the ending point over here you can see is it meets at 0 here, right? It meets at 0 and the y coordinate is 1. So you can have x end and y end is nothing but 0 comma 1. So this is our coordinate x1 y1 x2 y2 etc. Okay, so now instead of y, we have written it as mu. Okay, that is the only difference. So this is our x start, x end, etc. X start, x end, and this is mu start and mu end. Instead of y, I have just written mu because mu is the name of the y coordinate. Okay, now putting in the values, you know that mu of minus 2 is nothing but mu start. What is mu start here? Mu start is nothing but a 0. So you put 0 plus and x minus. In our case, x is for y. For this particular point, we need to find this value, right? So that is what we are trying to find out. So x is minus 2 minus and then we have x start. X start is nothing but minus 3 divided by xn. What is xn? Xn is a 0 here minus uh, again x start. X start is again minus. So we got this. Now into mu end minus mu start. So mu end is nothing but 1 and mu start is 0 because you know that the starting location is here and the ending location is. So first we have to write the ending location minus the starting location of the y direction. And finally we found that this is 0 and this is 1. So we can ignore these. So finally we have minus 2 plus 3 and 0 plus 3. It is nothing but 1 by 3. So that is how you got this point as 1 by 3. Similarly, you can find for the descending slope, apply the formula in the descending slope, and you can see that the first part, it will be subtracted. So you'll have a mu start here. So in the descending slope, the mu start is over here, right? So you have 1 minus, this same thing will be there, I think. Same thing. So in the descending slope, you have 1 minus minus 2 minus minus 3 divided by 0 minus minus 3 and into 1 minus 0. Okay, so this will be gone. So the entire thing that you got here, that is 1 by 3. The same thing is over here also. So you'll be subtracting 1 minus 1 by 3 that you get obtain 2 by 3 and that is the answer we got here. Okay, so these are the different ways of how you can get a particular answer. Okay, now so since only Mn and Zd has these non-zero values, there's one more thing that we need to understand, that is only the rules R2 and R3 will be fired because the rest of the rules are not applicable. We know that each of the rules were applicable. So only Mn and ZE is active, right? So only rule 2 and 3 will be firing. R1, R4 and R5 are not active. Okay, so will not be using them. So only rule 2 and R2 and R3 will be used. So now we have to map these membership values onto the corresponding D values. So we did not map it to the D value. This was a delta T. Now the same thing has to be mapped to the D value so that because what is the D value? D value is basically the consequent. This is the antecedent part and this is the consequent part. So we need to find the map these things onto the consequent part also. And that is known as the implication phase. So here usually we apply the min operator. So we'll see what is to be done. So the rule implication is the process that is illustrated in, we have to do this, I'll show you how it is to be done in figure 4.18 and figure 4.19. So this is 4.18 and this is figure 4.19. So the rule implication has to be done. So the first figure shows the process where the rule 2 has been applied and the second figure shows where rule 3 R3 has been applied. So in case of R2, the fuzzy membership of minus 2 with respect to the fuzzy set Mn, that is mu is equal to 2 by 3 was used to reshape the MP of the consequent part. Why MP? Because we know that rule 2 determines like this. When you have a value Mn, then the D should be MP, right? So we need to have a graph for MP onto which this particular mapping will be truncated. So we'll see how it is done. Okay, similarly for the second figure also, for that is in 4.19, ZE will be mapped to ZE of D. ZE of the graph that is 1 by 3, which was the coincident or the weight, you can say the weight or you also call it as the weight W. The weight or the mu value that you got will be mapped to the D value of ZE itself. So for the particular rule 3. Now after you do this, we need to find the area and the centroid of this entire thing so that the result of the implication can be carried out. Then only we get a particular result. So this is how we do it. You can see here, this is the graph that we saw earlier, and this is the new graph D that we have put into. So the D graph is from 0 to 1, we have a graph, and the value is it's also a triangle. This is also a triangle. Now for minus 2, we found out that the mu value of Mn where it intersects is 2 by 3, that is 0.666. So that same thing is mapped onto the D graph like this. Okay. Now you can see here this area that is cut off from this particular 2 by 3. That is, this is a trapezoidal value, and that is what is shown. Okay, this is the trapezoid that is shown separately in this case. So you have value that is here and it is mapped onto this particular area. Now, what will be the height of this? The height of this will be because we know that this was meeting at the point 2 by 3. So the height of this is 2 by 3. And that is what is shown here. Height is 2 by 3. And with a general idea of given the base is 1 and height is 2 by 3, we can find out that this is around 1 by 3. Okay, A is equal to 1 by 3. So the top base is 1 by 3 and the bottom base is 0 to 1. That is basically 1. So you have B1 is equal to 1 and if second base, if you call it as B2, then then you have 1 by 3. So this is the entire thing. Now it is easy for us to find the area and the centroid of this. Area of this trapezoid is basically B1 plus B2 into H. So that is nothing but 1 by 2 into 1 plus 1 by 3 into the height H, height 2 by 3. So when you finally try to find it, you get the answer as 4 by 9 and the centroid you get as 0.5. Centroid is basically the endpoints, this endpoint and then this endpoint divide by 2. So that is A plus B by 2 is the centroid, that is 0 plus 1 by 2 is nothing but 0.5. So that is the equation for the centroid and the area is given by 4 by 9. Okay, so for area 1 is given by this, centroid 1 is given as 0.5. Similarly, for the second figure also we have to find, we get the answer is 5 by 18 and centroid is equal to 0. Okay, so we look at the second figure, this one rule 2, rule 3, sorry. So when you're applying the rule 3, you get for -2, it was meeting at 1 by 3. So the height of this is basically 1 by 3 itself. And you draw a line on the graph D so that it is divided into this trapezoid like this. And that is what is shown here. Okay, so here also we find out that this is a almost 1 by 3, this is 1 by 3, and this is 1. So the area of this will be 1 by 2 into 1 plus 1 by 3 into 1 by 3, which get the answer as 5 by 18. And then the centroid is 0. Why? Because it is minus zero point 0.5 plus zero point 0.5 divided by 2, you get 0. Okay, the 0 point is acting as a centroid. So finally, when the rule implication has been done, and we had the result of two trapezoids like this, we have to finally aggregate it together. So aggregating it together, when you look at the diagram, it should look something like this. The figure is not given, but you can aggregate it together. Okay, so from 0 to 1, and um, after aggregation, it will look something like this. So this is 0 0.5, 1, minus zero point 0.5. So one of the graph you have like this at 1 by 3, and the second one is from 0 to 1 at 2 by 3. And the second one, just 1 second, is the height of 2 by 3 and varies from 0 to 1. Okay, so it's height of 2 by 3 and it varies from 0 to 1. So this way, you can see this is the entire graph after aggregation. So we need to find the uh, what do you say, we aggregate it together like this, and then we have to apply a defalsification using either the centroid method or center of sum methods or uh, mean of maxima method, any one of them. So suppose we are using the center of sum methods, this is how it is going to look. So we need to summation, or we do a summation of the area and centroid of each of the trapezoid divided by the sum of area. So we got the first one as 4 by 9 into zero point 0.5 as a centroid, then 5 by 18 into 2. So each one of the trapezoid, that is known as the center of sums. So what happens here is, in center of sum, I told in the previous lecture, like we'll have a disadvantage that this area is actually repeated by both the, because we are finding the area of this one and then we are finding the area of this one. Okay, so what happens is a few portion or the common overlapping area will be repeated in the center of sum. The area will be repeated here because we are adding them, multiplying and adding them together and doing like this. So we get an approximate value of 0.308. So what is the meaning of this? If you want to set the temperature T0, that is -2, if you want to set a particular temperature, we don't know what is the temperature. So we want to set the room temperature. Uh, so like this, when the room temperature is below the set temperature by 2 degrees, that is you got a -2, right? The delta T value. So that means you need to cool the room by that much. Then what happens is you need to put the AC dial, that is the position of D, at plus 308. So that hot air, because the room is already too cold, so it is in a negative value. So what you have to do is you have to move the dial to the positive direction, not too much, not too close to 1 and not too close to 0, so that the hot air will be blown into the room. So it should be moved to 0.308 so that the room will be uh, will be much more hotter than it is actually now. Okay, so that is the basic idea. So this is the answer of how the temperature can be controlled. Okay, now this is center of sums method. This has a disadvantage that you have overlapping area counted twice. Now let us look at another method, that is the centroid method. In the centroid method, the overlapping area will not be counted twice. Instead, I showed you aggregation process here, right? So this aggregation is what is done in the centroid method. In the other one, we separately calculate the trapezoid area and then we sum it together and divide it like this. But in a centroid method, we have the aggregation, that is outer boundary, is shown like this. Now this entire shape will be divided into either rectangles, left rectangle or right rectangle. Sorry, left triangle or right angle, you can say triangle, or you can have a rectangle of any shape, or you can also have a trapezoid of any shape, and so on. So this way you'll be able to divide it. Okay. Now we are going to divide it like this. So you have a what you say, a triangle here. Then you have another a rectangle here, that is ABJ is a triangle. Then BCIJ is a rectangle. Then CKIH is another rectangle. And CDK is a triangle. DEHG is another rectangle. And GEF is a triangle. So this is the basic idea. And we know the height of this portion is 1 by 3. And this is the highest one was the other trapezoid was 2 by 3, right? So we know the height and we know some of the positions, like we know where a 0 is there, we know where a minus 0.5 and plus 0.5, then we know where the 1 is. Because looking at this graph, we can know where is minus negative value 0, where is positive value, where is 1, where is 0.5, and so on. So based on that, the entire thing can be mapped like this. Now we need to find the area of each one of them individually and then uh, do the summation like this. The same summation divided by the sum of areas. Okay, that is the centroid method. So you can see in order to calculate this, we need to have, we do not know the exact division of these things. So we need to assume that, say, we can make a guess like this. That is, this starts at 0 and this is 0.5. Okay, 0 and 0.5. So this is actually basic division into 3 partitions like this. So I think the same thing also occurs here. Okay, so this is minus 0.5 till 0. And this is basically a 3 division partition like this, you can say. So you can say the point over here, when you have a value from 0 to 0.5 and you're dividing it into 3 parts, each part will be 1 by 6. Okay, so this is a 1 by 6. This is a 1 by 6. This is also maybe a 1 by 6. This is another 1 by 6. That is this particular part. Okay, so if that is the case, then what will be the x-axis coordinates here? If this is minus 1 by 3, then minus 1 by 2 plus 1 by 6, you'll get a value j as 1 by 3 here. Okay, and this is a 0. This we already know. And I point will also be 0, and the space length between this is 1 by 6. So I is 1 by 6. Then you have 1 by 6 followed by a one more length of 1 by 6. So this will be 1 by 3. Okay, and so on. And this is 1 by 2 followed by a 1 by 6. So when you add both of them, you get a 2 by 3 here. Okay, so let us, I'll just write it once again. The space between this and this is 1 by 6. This is 1 by 6, 1 by 6, 1 by 6, and 1 by 6. So the points here will be 1 by 3, 1 by 6, not 1 by 3, sorry, negative, because it's on the negative side, negative 1 by 3, 1 by 6, h will be 1 by 3. This is point 1 by 2 or 0.5. This will be 2 by 3. Okay, and this is 1. So now we got all the coordinates and we know the height of most of them on this side is 1 by 3 and this one is 2 by 3. So now let us find out of each one of them. So finding out the area, let us first find out the area of the uh, triangle. Okay, so area is given by half base into height, right? So half base into height. Now let us look at what is half. What is the base here? That is the base is basically AJ. Okay, AJ is the base. Okay, basically the base is AJ into height is basically the line segment. You can say the height of the line segment BJ. So what is AJ? We'll just map it out here. So AJ is minus the length. The first endpoint is minus 1 by 2 and the second endpoint is minus 1 by 3. So you can say it is So you can say it is minus 1 by 3 minus 1 by 2. The difference between both the endpoints. Sorry, my negative value is there. So let me erase this once again. Minus 1 by 3 minus 1 by 2. So both negative values, difference between both the negative values. And what is the height of this? The height of this is basically this particular length, that is nothing but we already know it is 1 by 3. So into 1 by 3. So that is nothing but 1 by 2 into this will become 1 by 2 minus 1 by 3 into 1 by 3. That is nothing but 1 by 2 into 3 minus 2 by 6 into 1 by 3. It is nothing but 1 by 2 into 1 by 6 into 1 by 3. We get the answer as 1 by 36. Okay, so the area is 1 by 36. Now let us find the centroid of this triangle. We know the equation for centroid is actually governed by these three formulas. So if you have a triangle that is facing a right side or a left side, the equations will vary. So the centroid will approximately come here. And how do you find this? Basically a plus b minus a. So a plus the difference between a and b divided by 3. When it is facing towards the left, you can say that it will be b minus. So this is the greater endpoint, b minus a divided by 3. So that is a basic idea. When it is a rectangle, it is simply this point a and this point b divided by 2. So remember these three formula, and that is what we are going to do. So in our case, it is a left facing triangle. So this will be our equation, b minus a by 3. So b minus a by 3. Let us write that b minus a divided by 3 is how we find out the centroid. Now let us, what is the value for b? B is minus 1 by 3 minus 1 by 3 minus 1 by 2, the whole divided by 3. When you solve this, what you're going to get is minus 1 by 3 minus 1 by 6 by 3 we get. That is nothing but around minus 7 by 18. You can solve it and find it will come around minus 1 by 3 minus 1 by 18 you get. That is nothing but minus 7 by 18. So you can see the answer. It's summarized into a table like this. For this particular, the area will be 1 by 36 and the centroid will be minus 7 by 18. Similarly, we have to find for others. So I'll show one more example for a rectangle and then I'll show you the result. So instead of doing each one of them, okay. So now let us look at how we can solve the area of a rectangle and the centroid of a rectangle. Okay, now let us take the rectangle BCIJ. Okay, it's a rectangle. So looking at the rectangle, you can see that um, okay, the height of how do you find the area of a rectangle is nothing but L into B. Now, what is the length of this and what is the breadth? So you can say, suppose this is the breadth that we are taking, then we say it is 1 by 3. Okay, the height of this is 1 by 3. And what is the length? That is the point JI, this point JI. What is the length of this? The length of this is basically, you can see the total length is, it comes around 1 by 6 is the point here, right? 1 by 6 and this point here is minus 1 by 3. This is 1 by 6. So j is minus 1 by 3 and I is 1 by 6. So how do we find the length? We have to write 1 by 6 minus 1 by 3 into. Okay, so this is how we are going to solve it. So the answer will be 1 by 6 plus 1 by 3 into 1 by 3 is nothing but 3 by 6 into 1 by 3, which is nothing but 1 by 6. So the area of this rectangle is 1 by 6. Now let us find the centroid. We can just look into the formula of the centroid once again. It is nothing but a plus b by 2. So a plus b by 2 is the same thing. Centroid a plus b by 2 is nothing but You can see the first point A is the point J, which has a value plus minus 1 by 3. And the second point B is the indicator I, which has a value 1 by 6. So minus 1 by 3 plus 1 by 6, the whole divided by 2. You get the answer as 1 by 12. Okay, so let us look at the answer. Yes, sorry, and there's a negative value, right? It is minus, so it will be minus 1 by 12. Okay. Now let us look at the answer. So the area of that rectangle A2, area A2, A1, A2 is divided into A1 to A6, the different areas for easy naming. And you can see it is 1 by 6 and it is minus 1 by 2. Okay, so this way we found out for the rectangle again. So, and we keep on doing this. So if you want, you can check another one also. Maybe this triangle or this rectangle. So eventually apply the formulas and you can find out the answers will narrow down to this. So we get all these areas and all these centroids of different partitioned triangles and rectangles, that is area A1 to A6. Okay. So for all these, we find out, now we have to find out the corresponding aggregate value of this. So in order to defacify this, what you have to do is we have to do the summation of each area into centroid by summation of each area. So this is what we have to do. So we take each of the value, that is, you can see here the values 1 by 36 into minus 7 by 18 plus 1 by 6 into minus 1 by 12 plus 1 by 18 into 1 by 4 and so on. So we take all of them, sum of all of them together like this and divided by the sum of the areas. So finally we approximate to a value of 0.227. So let us compare it with the center of sum. In center of sum we got a value 0.308. It's almost nearby but not so. So we'll get different answers. So to the positive direction, you have to move the AC dial to plus 0.227. Then only the temperature can be brought to the required temperature. Okay. Similarly, there's also mean of maxima. So mean of maxima we saw in the previous class is basically we have to find out the highest membership value obtained by all the points. So if there is only one point that gives you a maximum membership value, we just have to take that. But if there are multiple points, then we take the average or the mean of that. So find the points which gives the maximum membership value. So let us go back to the figure. We can see here the points that give the maximum membership value. You can see this is a maximum membership value, 2 by 3, right? So H and G are the points that gives you the maximum membership value. There are no other points. So what we do here is the value of H and G will be taken. So you know the point is from the origin. See this from the origin. What is the distance of these points? That is what we're going to find out. So you have 1 by 3 and 2 by 3. So the distances of H and G from the origin are 1 by 3 and 2 by 3 respectively. So that is why we find the average of that and finally we get the value as 0.5. So this is actually much more than the first two values. First one we got 0.30 something. Second method we got 0.22 something, but now we are getting 0.5. So the dial has to be moved to positive 0.5 in order to get the answer. Okay. So these are the different ways. Now we've added two extra YouTube links also for further reference.